In this video, we're going to take a look at section 5.1. Again, I just want to remind you, and as you take a look at these lecture videos, you print out the PowerPoints, you take notes for yourself. We're going to cover quite a bit of stuff, especially in this section. This section is pretty jam-packed about polynomial functions. So first of all, before we jump into this section, let's take a quick kind of look at where we've been and where we're going. So remember in Chapter 3 we talked about functions. We talked about functions in a very general manner. We talked about, let's say graphs of functions where they increase, decrease, max and min values. And then in Chapter 4 we talked a little bit more specific about linear and quadratic functions. So we graphed lines, we graphed parabolas, and we even looked at the word problems, right? The applications of both of those categories of functions. In Chapter 5, we're going to take a look at polynomial functions. That's what we'll do right now in 5.1. And then we're going to take a look at rational functions. Again, we'll look at the applications and some word problems that those classes of functions apply to. And then in Chapter 6, we'll wrap all of this up by looking at exponential and logarithmic functions. Excuse me. So to begin 5.1, the first thing we want to talk about just is kind of identifying the form of a polynomial function. And here's the standard form of a polynomial function. So just want to point out to you here, in this form, typically what we mean by polynomials, we have x's to an exponent, right? We have a variable x, and then we have an exponent, or a power, we might call it. And we have, even though this doesn't say it specifically, right, it says n is a non-negative integer. So what that really means is that it's a whole number, it's a counting number. So 0, 1, 2, 3, 4, 5, 6, so on and so forth. So these exponents cannot be fractions and they cannot be negative numbers. Right? And then the coefficients have to be real valued, right? So we say right here, coefficients have to be real valued. So we don't want complex or imaginary numbers. So a couple of quick examples, right? Here's a quadratic function from Chapter 4. This is a polynomial. Now because we talked about these specifically in great detail in Chapter 4, we won't really see them here in Chapter 5. But this is a second degree polynomial. Also, the lines that we graphed in Chapter 4, it technically is a polynomial function of degree 1. Again, we did those in great detail in the last chapter. I'm not going to really see those in this section. But those technically fall under the category of being polynomial. Here's another example of a polynomial equation. Notice we have powers of x that are non-negative integers, right? They're whole numbers. And then we have coefficients that are real valued. Okay. Here's another equation that would classify as a polynomial. Now, even though these are kind of mixed up, right, and they're not in decreasing power like all of these were written, technically that's still a polynomial function. Okay, and then even this factored equation would be polynomial. Right? If I were to FOIL all of this stuff out, I would get x squared plus 3x minus 10. So even though we, in this first slide, write polynomials in this kind of expanded form, if you will, polynomials definitely can be written in a factored form. And in fact, they're much more convenient to graph in a factored form because notice I can see the x-intercepts right here. Right? If I were to set the y value equal to 0, I could see x equals 2 would make the y value 0, and I see x equals negative 5 would make the y value 0. So we're gonna really prefer to deal with factored forms of polynomials whenever possible. So one of the first problems that you'll do in the homework is just looking at an equation, determining whether the equation is a polynomial, and then if it is a polynomial, what is its degree? So this first one, letter A, is this a polynomial? Yes, it is a polynomial. It has all real valued coefficients, and it has, whole number, right, non-negative integer exponents. So that definitely is a polynomial, and the degree is 4. That's the largest power. When I look at the second one is not a polynomial because when I write this as an exponent, this is x to the 1/2. Right? So remember that anything written as a root can also be written as a rational exponent. That's one of our properties of exponents. So that's not a polynomial. This is a rational exponent, not an integer. The third one would not be a polynomial either. Anytime we have an x in the denominator, that's actually a rational function, which we'll do later in Chapter 5. So that one's not a polynomial. Letter D is a polynomial. So this is like a horizontal line, y equals 0. Those definitely are polynomials. And technically we say that this has no degree associated with it. And then this one is a horizontal line as well, and it is a polynomial again, and it's degree 0. Now just real quick, I don't want to spend too much time on this, but just to show you the distinction between these two, the reason we say that this is degree 0 is because x to the 0, anything to the 0 power is 1. So 8 is thought of as 8 times 1, and I can write 1 as x to the 0, and so I identify this as a degree 0 polynomial. Now, the reason I don't identify this as a degree 0, this one a little bit tricky, because 0 times x to the 0 definitely is 0, or 0 times x cubed is also 0. So how do I think of y equals 0? Is it a degree 0 polynomial, or is it a degree 3 polynomial? It could be any of those. So that's why we say that there's no degree there. Okay? Anyway, so any horizontal line is a degree 0 polynomial. But again, we're not really going to deal with these in this section. We've dealt with them quite extensively in the past. All right, and then this last one would be a polynomial. So here's a factored polynomial. And notice if I were to FOIL all this stuff out, I'd get x cubed times x squared. So I'd get like a negative 2 times x to the 5th as the leading term here. And I'd have some other things being added. So for letter F, I'm going to say that that is a polynomial, and it is a degree of 5. All right, so let's go ahead and move on, and let's take a look at another concept in this section, which is that polynomial graphs are smooth and continuous. So up here in the upper left-hand corner, this would be the graph of a polynomial because it's smooth and it's continuous, right? So continuous meaning I never pick up my pencil, right? And smooth being it doesn't have any sharp edges, right? So here's an example of a graph that's not smooth. Here's a corner, right? Here's another corner. We call this a cusp, right? So I have two kind of edges on the graph. That's not smooth. And we have two places where I'd have to pick my pencil up to continue sketching the graph. So it's not continuous. Here I'd have to kind of jump over this hole to continue sketching the graph. So polynomials do not have these behaviors. They always look smooth and continuous. All right, now I jump back to this prior slide real quick just to say that ultimately here's the conversation we're talking about in this section. We want to be able to sketch the graphs of these polynomials by using tools of analysis. So I don't really want to have to take out my technology to graph these, right? Although I can, and although that is an option, what we're developing here in this conversation, right, as you as a student move through this class, is we're developing our tools of analysis. So what we're going to talk about in this section are some ways in which we can graph these polynomials without graphing technology. And then of course, we're going to use graphing technology to check our work. But we're going to ultimately develop our tools of analysis here. So the first tool of analysis that we're going to develop is what we're going to ultimately call the end behavior of the graph. Now, before we discuss end behavior, the author wants to point out to you, what a power function is. And basically, all a power function is a monomial. Polynomial term, right? So it's really a monomial here. I have x to a power and I have a coefficient, right? So here's 4 examples of some power functions. Here's a power function of degree 1, leading coefficients 3, power function of degree 2, leading coefficients -5, power function of degree 3, power function of degree 4. Now the reason that we're talking about this in particular is if a power function has an even degree, it's going to look kind of like a parabola at the ends of the graph. Right now, both ends are going to go off to the left and to the right. They're going to look kind of like a parabola at the end of the graph. And if the power function has an odd degree, it's going to go off in different directions at the end of the graph. Right? So that's ultimately what we're going to look at, the power function here. So there's a theorem that says that if we're looking at a polynomial in expanded form, the end of the graph looks like the power function, which is the largest term in this polynomial. Right? So if I just take the largest degree term in the polynomial, that equation represents, right, it resembles the end behavior of the graph. So again, the end behavior of this large expanded polynomial resembles the leading term. So what we're going to say is if that polynomial has even degree, right, if this polynomial has even degree, it's going to look like a parabola at the ends. Okay. Now, if this leading coefficient is positive, right, that's what we're saying right here, then it's going to open up at the ends, if you will. And if this leading coefficient is negative, right, if this leading coefficient right here is negative, it's going to look like a parabola, but it's going to be opening down at the end. Right? So this is really our first kind of tool of analysis. We should be able to look at the equation of a polynomial, and based on the degree, we should know that it's going to look like a parabola at the ends, and whether it opens up or down based on its coefficient. Now, if the degree is an odd value, it's going to go in different directions at the end of the graph. And if that leading coefficient is positive, it's going to kind of like increase as it does that in behavior. And then again, if the degree is odd, it's going to go in different directions at the end of the graph. And if the leading coefficient is negative, then it's going to kind of decrease. So this is our first tool of analysis, right? First tool of analysis, we should be able to look at the equation. Based on its degree, we know what it looks like at the ends of the graph. So using that concept, right, let's apply that to this question. So which of these graphs below could be the graph of this polynomial? We're going to only apply the concept of end behavior to answer this question for now. All right, so I noticed that the leading term here is y equals 1 times x to the fourth, right? So I noticed that the polynomial has even degree. So since it has even degree, it should look like a parabola. Now, it's either going to look like a parabola that goes off in the same direction, or it's going to look like a parabola that goes off in the same direction pointing downward. And that all depends on the coefficient, right? So since the coefficient here is positive 1, I know it's going to open up, okay? So I can see this graph definitely matches that. Here it looks like a parabola, both opening up. So this could possibly be the graph of the polynomial. Ditto here, right? Looks like a parabola at the ends, both opening up. This could also feasibly be the graph of that polynomial equation. And then letter C could match that as well. Right? Now letter D doesn't work, right? Because it doesn't match the idea that it's opening upward. Now we'll revisit this example in a couple minutes and we'll apply some other tools of analysis, right? But for now, the tool of analysis of end behavior, we would choose 3 of these graphs that could possibly match this polynomial. All right, now the second tool of analysis is what we call turning points. And the turning points are exactly what it is. It's where the graph turns and changes direction. If I look at this graph down here, it turns and changes direction. It's decreasing and turns and becomes increasing. Now in chapter 3, we called this a local minimum, right? We're still going to call it a local minimum, right? But in this section, they're attaching the term turning point based on the theorem that we have here. Here's another turning point, right? So we increase and we turn and change direction and we decrease, right? And there's a local maximum there. Now what the theorem says in this section is that if the polynomial has a degree of n, then the graph will have at most n minus 1 turning points. So in this example, here's a degree 4 polynomial. Notice how I have 3 turning points. 1, 2, 3 turning points. Okay. Now notice in this polynomial over here, again, this is a 4th degree polynomial, but it only has 1 turning point. Right? So the only thing we want to be careful of when we use this theorem is this theorem doesn't say that a degree n polynomial has exactly n minus 1 turning points. It says that it has at most n minus 1 turning points. So again, a degree 4 polynomial could have 3 or 2 or 1 turning points, but it can't have more than 3, right, based on this theorem. Okay. Again, another illustration. Here's a degree 3 polynomial, and it should have at most 3 minus 1 or 2 turning points. And here's an example where it has 1, 2 turning points. Here's another 3rd degree polynomial. Notice it has 0 turning points, right? It never changes direction. It's always increasing. So we're still satisfying that theorem. So in our tools of analysis, we could use end behavior and we could use the knowledge of turning points to quickly analyze some graphs. So let's revisit that example we did a couple minutes ago. So now that we have the knowledge of turning points, could we eliminate any of these graphs? All right, well, so we had originally circled A, B, and C based on the knowledge of end behavior. Now, if we think about turning points, right, here's a 4th degree polynomial. I know I should have at most 4 minus 1 or 3 turning points, right? At most that many. Now when you look at this graph, here's 1, 2, 3 turning points. So this one I could still choose, right? This one has 1, 2, 3 turning points. That one I could still choose. But take a look at letter C. It's got 1, 2, 3, 4, 5 turning points. So this one is no longer valid. So based on the knowledge and the analysis of turning points, letter A or B could feasibly be graphs that represent this polynomial. All right, now the third piece of analysis we're going to use are what we call zeros. And these are really x-intercepts. Right? So let's take a look at this for a second. So let's consider this polynomial that's in the expanded form. And if I look at the graph of the polynomial, here's what it looks like. So what I want to point out to you here real quick is a cool connection. It looks like -4, -2, and it looks like 3 is an x-intercept, right? Kind of hard to tell there. But what would be really nice is for us to have the factored form of the polynomial. So if I could factor this polynomial, here's what it looks like. And notice that -4 makes this factor equal to 0, and that is a y-intercept, right? Notice that -2 makes this factor 0, and there's I said y-intercept, sorry, there's an x-intercept. So I got an x-intercept of -4, x-intercept of -2. I can see those right in the factored form. And then x equals 3 would make this factor 0, right? And that's my x-intercept there as well. So what we're going to tend to notice in the bulk of the problems in this section is we're going to deal with them in a factored form. So much easier to analyze the equation in a factored form. All right, so in the textbook, here's that kind of official connection. So they say if f is a polynomial function and r is a real number, so that when I plug r into the equation, I get out a y value of 0. Right? Remember that that's an x-intercept, right? If I plug in r for the x value and I get a y value of 0, then that's an x-intercept. And so what we're attaching here, what's new in this section, we're going to call that number r a real 0 of the function. Some textbooks call it a root, right? So again, if r plugs into the equation and makes the y value 0, then r is an x-intercept of the graph. R is an x-intercept of the graph, and then that could come from the factor x minus r, just like we saw on the prior slide. Now, visually speaking, here's some things we're going to notice about polynomial graphs. We're going to notice that when we have x-intercepts, right, we have zeros, we could have a couple different types of behavior. So we could have the graph cross through the x-intercept, right, so it could go from negative values to positive values crossing through, or it could go from positive y values to negative y values crossing through, right? Or we could also have the graph kind of bounce off, touch the x-intercept. So it has like negative y values, hits the x-intercept, right, hits the 0, and then bounces back down again. So we can get some interesting behaviors at the zeros, and that's really the main purpose of this third piece of analysis that we're talking about. So let's discuss that a little bit deeper with an example. All right, so let's say in this example we want to find a polynomial of degree 3, and the zeros are -4, -2, and 3. So if I'm given the zeros, then I know the factored form of the polynomial, right? So if -4 is a 0, then I know I need to be able to plug -4 into the equation and give me 0 times anything, which is 0, right? So if I plug -4 in here, I'm going to get a y value of 0. If I plug -2 into this factor, I'm going to get a y value of 0. If I plug 3 into this factor, I'm going to get a y value of 0. So here's a representation of the polynomial that has these 3 zeros. And I wrote the polynomial in a factored form because that's by far the easiest form to use. Now, I also want to point out to you that it doesn't really matter what number I pick as my leading coefficient here. This could be the number 12, this could be the number -7, doesn't really matter. These factors still produce the 3 zeros given. Right, so for example, suppose I pick 1 as that leading coefficient, right? If I pulled out my graphing calculator and graph that, that's what I see. I see -4, -2, and 3 as my zeros. If I make this leading coefficient -1, I still get -4, -2, and 3 as my zeros, right? So even with that leading coefficient of -1, right? And then I made the leading coefficient 2. I still get the same zeros, -4, -2, and 3. Right? So this leading coefficient doesn't really matter what it is. Now, granted, it does change the end behavior, right? So when this is negative, I see the graph is starting above and then it's kind of decreasing to the other end, right? So the sign of that number changes the end behavior, but it doesn't change what the x-intercepts actually are. All right, now in this conversation of zeros, one other thing we need to add to that is this concept that we call multiplicity. And basically, here's what multiplicity is. Multiplicity is the exponent on the factor. Now keep in mind, what does the exponent really mean here? Right? Remember, exponents are just a shorthand, lazy way for us to represent multiple products. So x plus 1 times x plus 1 times x plus 1 is really what x plus 1 to the third power means. Okay, so this is what we mean by the term multiplicity. X plus 1 cubed, this is the multiplicity. This tells me that the factor appears multiple times, 1, 2, 3 times. So what we'll do then in this last piece of this conversation of zeros is we're going to talk about the multiplicity of each zero. So for example, for this polynomial function, x equals 2 comes out as a 0. So if I look at this first factor, x minus 2 equal to 0, x equals 2 is one of the zeros. And then the exponent on that factor is a 1. So we're going to say it has multiplicity of 1. Then the next 0 we would get is negative 1. So if I set x plus 1 equal to 0, I get x equals negative 1. And we're going to say that the multiplicity of that 0 is 3. Because again, it appears 3 times as a factor. And in this last factor, right, again, we're going to get the 0 of x equals 3, and we're going to say that has a multiplicity of 4. Now, what is the purpose of that conversation? Well, the behavior of the graph is going to change based on its multiplicity. And here's what we're going to see in general. If that exponent, right, the multiplicity is an even number, the graph is going to bounce off, or what the author calls touches. So this would be a 0 that has an even exponent, an even multiplicity. And if the multiplicity is odd, the graph crosses or passes through, if you will. Right? So if the exponent on the factor is odd, the multiplicity is odd, then that's the behavior we're going to get of the graph. So as we develop our analysis, those pieces of information are going to be able to help us sketch a pretty good detailed picture of the graph. Now, if we jump back to that last example that we had where we had x equals 2 and the multiplicity was 1 because of that exponent, right? We had x equals negative 1, multiplicity is 3, x equals 3, multiplicity is 4. So I pulled up a graphing calculator real quick, graphed it, and grabbed a screenshot. We can see that at x equals 2, the multiplicity is an odd number. The number 1 is odd. So out here at x equals 2, the graph is crossing through, as it should with odd multiplicity. X equals negative 1 has a multiplicity of 3. That's an odd number. So over here at x equals negative 1, the odd multiplicity crosses through, as it should. At x equals 3, the multiplicity is an even value. So we can see out here at x equals 3, the graph is bouncing, right? What the author calls touches. So in our analysis, those are going to be some really quick things we can develop and sketch on the graph based on the multiplicity of the zeros. Now, if we real quick look at another example, here's an example where I'm being given a graph over here on the right, and I'm being asked which of these equations would match that graph. Now, what I don't really want to do is pull out my graphing calculator and graph all 4 of these, right? I don't want to graph these on Desmos.com and then pick the one, right? I want to use my tools of analysis. So what I'm noticing on this graph, right, here's x equals 0, x equals 1, and x equals 2. Those are my x-intercept. Those are my zeros, right? Now, all 4 of these equations match that idea. If I plug x equals 0 into this equation, I get 0 times whatever, and it's 0. And that's true for all 4 of these. X equals 1 is a 0. So if I plug 1 in here, here, I'm going to get 0 for a y value, right? So all of these equations have the correct factors. It's the multiplicities that are changing. So it looks like at x equals 0, the graph passes through. So I need to have odd multiplicity there. So notice this has even multiplicity and this has even multiplicity, but letter C has odd and odd. Those are exponents of 1. So far, only letter A and letter C should match this graph. right? And then let's look out here, I guess, this guy right here. So at x equals 2, this should also have an odd multiplicity. But I can see right here, this factor has an even multiplicity. So letter A can't be the answer, has to be letter C as a by process of elimination. And then let's just connect with this factor, right? So x equals 1 is a 0. Notice that it's bouncing, it touches. So that should have an even multiplicity, and we definitely have that there. So of the 4 equations given, based on our analysis of zeros and their multiplicities, we would choose letter C as the equation that matches that graph. All right, look, let's do one more example here where we kind of put these tools together. This question says, which of the graphs could be the graph of a polynomial function? Right? For those that could be the graph of a polynomial, list the zeros and then state the least degree the polynomial could have. Right? For those that could not, say why not. So for letter A, when we look at letter A, notice this graph is not continuous. There's a break in the graph. So right away, I know this graph is not the graph of a polynomial because it's not continuous. And when we look at letter B is smooth and continuous, so this could be a polynomial, right? So I'm going to say this could be a polynomial. Looks like the zeros are -2, 1, and 2. And then what's the least degree the polynomial could have? So what I'm going to have to do here is use that turning points idea. Since there's 1, 2 turning points, I would say that this could be a degree 3 polynomial. So that the degree of 3 gives me 3 minus 1, which is 2 possible turning points on that graph. All right, letter C, again, can't be a polynomial, right? Because it's not smooth. So it is continuous, but it's not smooth here. So that's not a polynomial since it has a corner. And then what about letter D? So it looks like letter D is relatively smooth and continuous, so that might be a polynomial. And it looks like the zeros are -2 and 1. And then what are the degree, the least degree the polynomial could have? So let's see, it's got 1 turning point, 2, 3 turning points. So it could be a degree 4 polynomial or more. All right, and again, what I like about this problem here is that we don't have any equations of polynomials, right? We can't take out our calculator or go to Desmos and plug it in and graph it. We're using our tools of analysis to analyze graphs, and that's ultimately what we're trying to develop here in this section. All right, so the last piece of analysis that we're going to develop here is what we will call kind of focusing in on the zero and talking about the behavior near the zero. So in this example, what we're doing is we're looking at this polynomial right here, which is y equals x squared times quantity x minus 2. And we're kind of zooming in on the x-intercept of x equals 0. And we're noticing that this parabola, -2x squared, looks almost identical to the polynomial. So here's basically what we're going to do. We're going to say, in order to figure out kind of what the graph looks like near an x-intercept, we're going to literally plug the x-intercept in, right? Now here's the difficulty, right? So if I look at this equation here and I notice x equals 0 is an x-intercept. If I plug x equals 0 into here, I get 0 times -2, and I get a y value of 0. So what I end up doing, and here's kind of the trick, I don't plug 0 into this factor, but I plug 0 into this factor. So if I plug 0 into here, I get -2 times x squared, and that's the graph that the polynomial resembles near the 0. So the work that I would do, again, I would plug 0 in, I plug the x-intercept in to every factor except the one that it would cancel out. And that gives me the equation that the graph resembles near that x-intercept. Right? Now if we look at the other x-intercept on that graph, let's look at this one over here, kind of looks like a line if I zoom in. So here's what we're going to do, right? So if x equals 2 is the x-intercept, I can't plug 2 into both factors, because if I plug 2 in here, I get 2 minus 2, which is 0. So what I'm going to do is plug 2 into the other factor. I'm going to plug 2 in here, I'm going to get 2 squared, which is 4, but I won't plug it into this factor. Well, you know, guys, this is a typo here. This square should not be here. Okay, so this should be 4 times x minus 2 to the first power. Right? So that is a typo. Let me fix that. I apologize. Okay. So this should be 4 times x minus 2. So it looks like that line, 4 times x minus 2. All right. So the last piece of analysis that we'll develop here is getting a little bit more granular in detail and talking about how the graph behaves near the 0. The trick basically is we're going to plug in the x-intercept into the equation, but we can't plug it into every factor. We're going to plug it into every factor except the one that it would turn into 0. All right, so again, we're using our tools of analysis. The multiplicity tells us whether the graph, crosses or touches. And then we can develop an equation that tells us a little bit more detail about exactly how the graph touches. We can write an equation that describes that for us. All right, so let's take this a little bit deeper and look at a specific example. Let's say here's an equation of a polynomial, and let's determine the behavior near each 0. So the first 0 that I see here, just in order of the factors, is x equals 0. So I know that when x equals 0, y is 0. That's an x-intercept. So if I want to find the equation that represents the behavior there, I'm going to plug x equals 0 in to every other factor except the one that it wipes out. Now again, the multiplicity on this 0 is exponent of 1. So because the multiplicity is odd, I know the graph is going to pass through. But exactly how does it pass through, right? What would that look like? So I know that at x equals 0, I'm going to plug 0 into every factor except the one that it would 0 out, right? And I'm going to get negative 4 squared, which is 16, times 1, which is still 16, times the 2, which is 32. So it's going to look like the line that has a slope of positive 32. Now the next intercept of x equals 4, right, again, I'm going to plug 4 into every factor except this one. So that's what I'm doing here. And I end up getting 200 times x minus 4 squared. So this looks like a parabola shifted to the right 4 units, and it's been stretched vertically by a factor of 200. Very, very stretched. And then the third one, again, this third factor has a multiplicity that's even. I know it's going to bounce at that x-intercept, but exactly how does it bounce? So we plug negative 1 into every factor except that factor, and I'm going to get negative 50 times x plus 1 squared. So this looks like a parabola shifted to the left 1 unit, and it's reflected upside down. So here's rough sketch of what those 3 x-intercepts might look like. At x equals 0, here's my line with slope 32. At x equals 4, here's a parabola, right? Opening up, sorry. And then at x equals negative 1, here's a parabola opening down. It's a rough sketch on pencil paper, and then I took out a calculator and graphed it. And I notice a calculator struggles with these really big numbers here, but I can kind of see, here's the bouncing. Right? Here's the passing through. It's kind of hard to see that. And then here's the bouncing up as well. One thing you'll notice is that Desmos does a little bit better of a job kind of smoothing out the curve. The calculator struggles with that a little bit. Okay, so we're almost done here. I just want to do a couple more examples with you to kind of pull all of this information together and put it all together in a couple problems. So in this example, I'm giving us the equation, I'm giving us the graph, and I'm not giving us the equation. So from the graph, right, we're going to analyze information about the polynomial. So question 1 says, referring to the graph, how many turning points does the graph have? So I can pretty easily see 1, 2, 3 turning points on that graph. And number 2 says, does the polynomial have an even degree or an odd degree? Now, a couple different ways I can determine that, but I think the easiest way to determine that is to look at the end behavior. So at the ends, the graph goes in the same direction, kind of like a parabola. So it has to have an even degree overall as an entire polynomial. Okay. And then again, we notice the coefficient must be negative, right? Because remember, if the coefficient was positive, I would go upward at both ends. Number 3 says, what are the x-intercepts of the polynomial? So again, as we've talked about, right, here is an x-intercept at -4, here's an x-intercept at 0, here's an x-intercept at 3. And those x-intercepts, those are what we're going to call our zeros as well. So number 4 says, find the zeros and tell their multiplicities, right? So at this 0 of -4, the graph crosses through, so it must have an odd multiplicity. At this 0 of x equals 0, it bounces, right? It touches, so it must have an even multiplicity. And then over here, this 0, it's crossing through, so it must have an odd multiplicity. Now, number 5 says, suppose that we want to write a 4th degree equation that could represent this graph. Right? Now remember, up here we had said that the polynomial had an even degree because it looked like a parabola at the ends, and this is kind of confirming that for us. This is saying write a 4th degree polynomial. Right? So this is really pretty straightforward in the sense that I have all of the zeros, so I know the factors. Right? So since I know x equals -4 is a 0, I know x plus 4 has to be a factor. I know that x equals 3 is a 0, so x minus 3 has to be a factor. Right? And then I also know that x equals 0 is a 0, and it has an even multiplicity. So I'm going to make that factor have an even exponent. So here's the 0, the factor for 0, -4. Here's the factor for x equals 0. Here's the factor for x equals 3. These have to have an odd exponent, the first one and the last one, because the graph passes through. This has to have an even exponent because the graph is bouncing. Now again, we said this was going to be a 4th degree polynomial, so we can see that x squared times x, that would give me x to the 4th. Right? And then we talked about the end behavior, the end behavior where the graph points down, right? Tells me that it's an even degree polynomial altogether. So there's our 4th degree polynomial altogether. And then again, because it's pointing down, we have to have a negative coefficient. So I just put -1 in front so that we satisfy that relationship. All right, so let's do one last example similar to what you're going to see in the homework. All right, so in this example, it says, find the x and y intercepts, determine the graph crosses or touches at the intercepts, what's the end behavior, what's the maximum number of turning points, and then determine the behavior of the graph near the intercepts. Put all this information to sketch the graph. I want to point out to you this polynomial is not given to us in a factored form. So what we're going to do first is we're going to factor this polynomial. All right. So when I find the x and y intercepts, right, I'm going to go ahead and factor that polynomial. So I take out the common term of x, and I'm left with x squared plus x minus 12, and then I factor x squared plus x minus 12 as x plus 4 times x minus 3. Right? So that gives me my x-intercepts. So I'm going to have 0, -4, and 3 as my x-intercepts. Right? And notice the y-intercept I already found. Right here is my y-intercept as well. Now letter B says determine whether the graph crosses or touches the x-axis at each x-intercept. So what we're going to have in this case, right, this is a multiplicity of 1, that's its exponent. This is a multiplicity of 1, and this is a multiplicity of 1. So because all of those x-intercepts have an odd multiplicity, they're going to all cross. Right? All factors have odd powers, so each 0 has odd multiplicity. The graph will cross at each x-intercept. So we don't have any bouncing or what the author calls touching at any of the x-intercepts. So letter C, we were asked to find the power function that resembles the end behavior. Now, that's pretty easy in the sense that it's my leading term. So y equals x cubed represents the end behavior of the graph. And remember, what that means is if I were to sketch the graph, let me turn my pen on here. If I were to sketch the graph, right, it looks cubic at the ends, and because the leading coefficient is positive, right, it's going to go in opposite directions here, right? So I got the graph going in opposite directions based on that leading term. All right, letter D said determine the maximum number of turning points. So again, from that theorem, we know that the degree is 3, so we're going to have the maximum being 1 less than that. So we have 3 minus 1, or 2 possible turning points at the most on that graph. Letter E says determine the behavior of the graph near each x-intercept. So again, we're going to plug in each of our x-intercepts into this factored form of the equation, except for the factor it zeroes out. So when I plug 0 in, I'm not plugging it into this first factor, but I'll plug it into these two, and then I'll repeat that. When I plug -4 in, I'm not going to plug it into the second factor, but I'll plug it into the first and the last. All right, so at x equals 0, I'm going to get y equals -12x. That's what the graph will look like, a line sloping downward. At x equals -4, I'm going to get y equals 28x in essence, right? So a line with positive slope. Right? And then at x equals 3, I'm going to get y equals 21 times x minus 3. So if I were to put all of that together, first of all, here's my three x-intercepts, -4, 0, and 3. And then here's the end behavior. Here's my cubic end behavior. So just kind of putting the first two together there. And the next thing I kind of did was I sketched the behavior at the intercepts. So at x equals 0, here's the line with slope -12. So right here, like here's a line with decreasing slope. At x equals -4, right, here's the line shifted to the shifted to the left 4 units with a slope of 28. So here's a line shifted to the left 4 units, slope of 28 roughly, right? And then lastly, this guy as well, kind of what that might look like. So piecing that together, and then knowing the last step here, knowing that the graph has to be a smooth, continuous polynomial, I need to connect all of this, right? So roughly, right, if I take out my digital pen one more time, roughly I got to connect all of this information. I know I got to turn around somewhere here to hit that guy, and then turn around somewhere here to hit that guy, and connect it all together. And so there's a rough sketch of that polynomial. All right. Now, even though I just said this is a rough sketch, this is actually really detailed. We have some really good detail about the behavior of the graph. The only thing we're really missing here is where the graph turns around. So like, what is the y value here? We haven't found that y value, and we're not really going to typically be asked for that information. Here, this turning point, right? That's a local minimum. What's that y value? We don't really know. And notice that I haven't scaled my y-axis. So I didn't put tick marks on here implying that I know where that y value is. It's probably pretty far up, to be honest with you. And until I take out a graphing tool, I don't really know where that is. And we're okay with that. We're okay with our analysis leading us to this pretty good detailed sketch of the graph. All right, and on this one last example, I'm going to move through pretty quick because I think you guys are probably starting to get the hang of this, and you really need to get into my math lab and practice this on your own. Me, lecturing this to you isn't the best way to learn it. So you got to get into my math lab and really practice this stuff. But I want to look at one last example here for your notes and give you the polynomial in a factored form. So in the prior example, we had to factor the polynomial. In this one, we don't have to. So know this is factored already. It's going to make things much, much easier. So when I find the x and y intercepts, it's really easy to do that first, right? Because the x-intercepts are going to come right from the factors. So x equals 0 will be an intercept. X equals 4 will be an intercept from this factor. And x equals -1 will be an intercept from that factor. So pretty easy to match what those x-intercepts are. And then, in this case, I actually found the y-intercept when I found the x-intercept. Right? And then determine whether the graph crosses or touches the axis. Now again, this is an even multiplicity, so it's going to touch at that x-intercept. Right? Let me point down here. This is an odd exponent, so it's an odd multiplicity. It's going to cross through at that x-intercept. And this has an odd exponent, right? A 1 as an exponent, so it's going to cross through here as well. So x equals 0 has the even multiplicity, the graph will touch, and then the other two have an odd multiplicity, the graph will cross through. Letter C says find the power function that resembles the end behavior. So for this one, this is a little tricky in this case because it was given to me in a factored form. I kind of have to envision if I multiply all of this out, what's the leading term? It's not that difficult, right? But I'm going to basically have x squared. Here's x squared times x, which is x cubed, times this x, which is x to the 4th. So y equals x to the fourth is my leading term. So that's going to be my end behavior, my power function. So the graph's going to look like a parabola shooting off in the same direction. And because the leading coefficient's positive, it's going to point upward. All right, letter D says determine the maximum number of turning points. There's a fourth degree polynomial, as we just discussed in letter C. So we're going to have at most 3 turning points. Right? Could have fewer, but we'll have at most 3. And then letter E says determine the behavior near each x-intercept. Right? So just like we talked about in the prior couple of examples, right? At x equals 0, I'm going to plug 0 into all the other factors. And so I'm going to get negative 4 times x squared. So there's my bouncing that I see there. And then x equals 4, I'm going to plug into the other 2 factors, except the one that it makes 0. And I get a line, y equals x, with a positive slope of 80. And then the last x-intercept, I would do the same thing. All right, now I didn't have any room left on the slide to put the graphing, so let me go to the next slide here, and we can see there's my graph, and we've labeled all the information. All right, so here's the end behavior. It looks like a parabola at the ends. Here's the 3 x-intercepts. Here's the line, the parabola, and the line that we got. And then if we fill in the gaps with a smooth continuous curve, there's the graph of our polynomial. All right, so again, even though we are looking at the specifics of graphing a polynomial, keep in mind that you aren't really supposed to use your technology here. Although we do have it, and we should use our technology to check our work, the ultimate conversation here is that we're learning to analyze. So given the equation of a polynomial, right, step 1 would be find the intercepts. Step 2 would be determine whether it crosses or touches at the intercepts. Step 3 would be determine the end behavior. Step 4 would be determine the turning points. Then 5, determine the behavior near the intercepts. And then step 6, put it all together and obtain the graph of the function. And then after you've analyzed and put all that together, take out your technology and check your work. All right, I know this was a long video. I apologize. This was a jam-packed section. If you have any questions as you work on my Math Lab homework, as always, make sure you post on the discussion board in Blackboard, and I'll see you in the next video.